Okay, so last time we talked about how hard a ball is hit on average, but we didn't answer the question of how hard it needs to be hit to exit the ball field. Do you think I'll answer that question this time around? Stay tuned. Hey, sports fans and nerds alike, I am Cleet Callahan. Thank you so much for tuning in to episode 3 of Baseball Physics, where I discuss baseball and physics alike, because I like both of those things. And if you are here watching this, then you like both of those things as well, or you just like me, and in which case I like you too. Last time we found that with an exit velocity of 104 miles an hour and a pitch speed of about 93 miles an hour, we exerted a force on the ball of 18,857 newtons of force. Holy smokes, but how far will that ball go? Well, that depends on a few factors. Those factors being the launch angle, the bat speed, and the physical materials of the bat. Now, according to the Washington Post, the sweet spot for a launch angle to result in a hit is between 25 and 35 degrees, okay? So anything more than that will probably be a pop-up or a fly-out, and anything lower than that is probably going to be a grounder to the shortstop for a double play, and we don't want to see that. Exit speed is hugely important, and we should discuss how to calculate it. Fancy scientists found a formula. It is exit velocity equals Q times the pitch speed plus 1 plus Q times the bat speed. Simple enough. What's Q? It stands for quiche, an eggy treat. That's not true. Q is the variable for collision efficiency. Say it with me, kids. Collision efficiency. In other words, it's how well the bat takes the ball and pushes it back out. Most Major League wooden bats have a collision efficiency of 0.2. Okay, so the average bat speed in 2019, according to blastmotion.com, is 70 miles an hour, or with the conversion, 31.29 meters per second. Yeah! So using our other data, let's see what the average exit velocity of 2019 would be. Okay, so using our formula here, we have exit velocity equals Q times the pitch speed plus 1 plus Q times the bat speed. All right, great. What do we have so far? We have a bat speed of 31.29 meters per second. We have a pitch speed of 44.66 meters per second. We have an exit velocity of 46.48 meters per second. Great. We have a Q of 0.2. We have a force of 18,857.14 newtons. We have a mass of 0.145 kilograms. We have a time of impact of 0.0007 seconds. We have an acceleration of, I don't know yet. Okay, so using the formula of F equals ma and converting it to A equals F over m, we calculate that the bat experiences an acceleration of 129,158 meters per second. That is 13,000 times the acceleration due to gravity. Okay, now I feel compelled to add one more number to the conversation. Might I say I feel an impulse to tell you about impulse? Yes, that's right, impulse. Impulse is the product of the average force and the time the object is experiencing the force. Not that force. So if we take the force of 18,857.14 newtons and multiply it by the 0.0007 seconds of the contact between the bat and the ball, then we find an impulse of 13.2 newton seconds. That's the way the units work out, newton seconds. So however, that 13.2 newton seconds is more or less a summation of the forces of the bat and the ball as they're touching. The instant the ball touches the bat, there's an inconsequential amount of force Okay, it's barely touching. The atoms are just barely touching each other. And then as the ball hits it, it squeezes in there and more force is exerted. And then it kind of releases a bit more and it goes in and it lessens up and it bounces the other way. And that will be a parabola, okay? If we were to chart the force and the area underneath that curve is the impulse. Okay, the maximum amount of force will occur when the ball is literally squished up against the bat. Okay, sometimes you could even see the ball squished to about half of its radius. It is in that collision that the ball loses some of its energy. The actual warping of the ball around the bat, there is friction and there is heat energy lost, and the ball then uses its remaining energy to return to its normal shape. The bat will bend also, by the way. If the wall of the bat just gave a little bit more, it's like with an aluminum bat, then the ball wouldn't need to expel so much energy to squish. Does that make sense? The energy will morph the bat's shape much more. Some aluminum bats have a collision efficiency of upwards of 0.55. All right, 0.55 times 44.66 plus 1.55 times 31.29, blah, 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 blah. 163 miles an hour off the bat. That is why aluminum bats are not allowed in the big leagues, because someone's face could rip clean off. So how do you hit a home run? That's all we want to know, is how do you hit ding-dongs? Okay, firstly, 57% of all the balls hit for home runs in 2016 in that Washington Post article that I linked below, they were hit in the sweet spot of 25 to 35 degrees of a launch angle, and all had an average exit velocity of about 95 miles per hour. So does that mean that every ball that has a launch angle in that sweet spot with an exit velocity of 95 is hit for a home run? Not necessarily, because you have such factors as air resistance, drag, friction, spin, wind velocity, bat mass, blah, blah, blah. They all need to be taken into account for the real world consideration of how to hit a dinger. There's a fantastic study done where they calculate exactly what is required to hit dingers. It's a little over my head to explain, but check it out if you're interested, okay? We can talk about if it's in a vacuum, right? Meaning if there's no air. If we are just in the vacuum of space and we have these parameters, can we at least figure that out? I think so. How far will the ball go using the variables we have in a vacuum? And tune in next time, because that's when we're going to figure it out. Oh, come on, Cleet! You can't answer the the question in the video that you gave me. Sorry, we're running out of time, but tune in next time. Thank you so much for tuning in to the episode. Okay, like me on Instagram, Facebook, and Twitter at Cleet Callahan. Go ahead and click that subscribe button and like this video and comment below if you have questions, comments, concerns, or points of interest about things or stuff. Watch me play video games on the internet, twitch.tv/playbyplay. That's our show. Tune in next time. We're going to answer this question, I promise. We'll see you at the ball game or the classroom or wherever.